Good morning, gang. Hope this finds everyone well. I wanted to make a quick tutorial on what you're doing with statistics. So I know it's been a long time since we had statistics, and a lot of you are probably wondering, what am I doing? What am I even writing about? So let's talk about what we've done. All right. So many of you have run either a correlation, a t-test, or an ANOVA. And so a couple of you may have chi-square, and I'll go over that individually with you. But for the most part, most people are doing like correlation, and maybe a couple people do multiple regression. But let's talk about what that means. All right. So when we do correlation, I've got this mistitled, regression and or correlation. Basically, they're doing the same thing. But correlation gives the percentage of a shared relationship. Okay. So for instance, going back to statistics, ice cream sales tend to go up, and violent crime sales go up. And so I won't give away the third variable there that's involved, but they tend to go up at the same time. And so the blue part of this graph would represent the percentage of relationship between ice cream sales and violent crime. And so what I mean by relationship, you have to look at a scatter plot. And so, for instance, we could have ice cream sales right here and violent crime numbers here. Either way, you could have violent crime numbers represented over here, ice cream sales represented over here. Either way, it doesn't matter. So, for instance, we're plotting shared incidents here. So let's say we're looking at a day when we had violent crime and we had ice cream sales of about 0.25. So we had this much violent crime and this much ice cream sales. Then we go down and we keep going, and we have another day, and we have ice cream sales about 1.2, and violent crime about 0.75. And then we go another time, we measure violent crime again, it's 0.125. And now ice cream sales have gone up this much. We go measure another data point, and now we see violent crime numbers are 1.75, and now ice cream sales are 1.6. We're like, wow, what's going on? And then we go all the way over here to another day, and ice cream sales skyrocket to almost 2.5, and violent crime's about 2.5. See how when one goes up, the other goes up. There's a shared relationship. And so we can report on that. So when we're doing a correlation, that's what we're really looking at. And so by doing a Pearson correlational analysis, we can say it appears that ice cream sales significantly predict violent crime. So you have an R number here. That's what your actual statistic tells you is 0.56. And it'll also give you a probability. In this case, it gave us a probability of 0.01. So if we go back up here, you can see this is roughly 56% of this whole pie chart. That's basically what this is, this 0.56 number behind the R. It's telling you the percent of the relationship that's shared. So this line and this pie chart would basically give you the idea that there's about 56% of a shared relationship here. Now, what we didn't say here is that, well, look, boy, it looks like people are eating ice cream and killing people. Well, that's not really what's going on. We do know that that when the temperature goes up, when the temperature goes up outside, ice cream sales tend to go up and violent crime rates tend to go up. So it's hard to make a causal relationship. You can't say that people eat ice cream and go kill somebody. Now, you could probably try to measure that, but not this way. This is a correlational analysis. It's only looking at relationship. It's good to predict things. It's good to be able to predict things. It's not saying one causes the other, but it's basically giving you, saying that, there's about a 56% shared relationship there. The orange part of this pie chart would say other factors in violent crime. What you would see probably largely overlap is if we did the same study looking at violent crime and outside temperatures, you'd probably see a big overlap with the ice cream sales too. So it would probably be the same blue area. Okay, so that's correlation. Let's move on quickly to a t-test. So a few of you are looking at t-tests, and we're examining differences between groups. So now we're not looking at a shared relationship. We're trying to examine a difference. Is there a statistically significant difference between two scores? And so we'll also report this thing called a p-value. And a p-value represents probability. So when you report a p-value, let's say of 0.01, it means that the score you found is statistically significant. It means that the score you found, if you're looking at the bell curve, would be out here on the right-hand side. Or you could also say on the left. But in this case, over here on the right-hand side of this, 99% of scores would be below that number. So again, you'd have a very remote chance of making an error, okay? It is one of the tails of the curve, meaning that there is a very small probability you found it by chance. 99% of all other scores would be closer to the middle of the curve back here. So you can see that they give you that probability score here as well. So it's basically telling you this big time relationship between ice cream sales and violent crimes, 56%. It's statistically significant. In other words, if you looked at other factors, let's say somebody's name is Fred and violent crime, you'd expect that to be here in the middle of the curve. So if you explored other variables, you would think that there'd be no relationship. But because of that high R value, R equals 0.56, we got this high probability. The same thing goes into a t-test. T-test, though, you're projecting that score directly into this distribution. So here is a hypothetical t distribution. Really resembles the bell curve. Let's say in this case that we're now looking at differences between groups. So that's what a t-score does. It looks at differences between groups. If you're running a t-test, you're examining the difference between two averages or means. Okay, so let's take this hypothetical experiment, okay? We're going to give a relaxation activity to a group of students, and another group of students, we're not going to give them that relaxation activity. Then we're going to measure their levels of anxiety after that relaxation activity, or just after not giving them the relaxation activity. So let's say we did that. And so, for example, anxiety scores of students who were given a relaxation activity, their anxiety score was 3.2. That's pretty low. Anxiety scores of students who were not given the relaxation activity were a little higher. They were 4.5. They have a little more anxiety. So what we did when we compute a t-test, it'd be appropriate to do a t-test here, we would compute the probability that the difference between scores was found by chance. And then you're able to actually locate the t-score on a curve. So when I want you to visualize this, when you're reporting a t-score, this is what you're actually reporting and what it should look like in your head. So for example, if you got a t-score of 3.1 or negative 3.1, you can get negative t-scores. T equals 3.1 would be located where on this distribution above? So if you're looking for 3.1 on this distribution above, where would you find it? Out here in the tails, or negative 3.1. So again, thinking about probability, if you had a t-score of 3.1, what's the probability that you found that by chance? Well, it's pretty remote. I mean, you look at the same thing, that we just talked about up here, about 99% of this of scores that would be lower than that. So let's say you got a t-score of 1. That's not statistically significant. Anything around between 0 and 2, generally not statistically significant. It means, you might have been over here. It might have been a little bit higher if you're considering all scores that you could have found, but it's probably not significant. However, if you get out here in the tails, t-scores of about 2, 2.5 or higher, really that's a good thing. You're out here in the tails, and you probably found a significant difference. So, for example, T 3.1, a t-score of above 2 has a good chance of being significant if your sample size is big enough. Your t-score is really dependent on how many people you got in your survey, which is why I really, wanted people to get at least over 30. So if you don't, then it takes a lot to really find a difference. Here is how you would report that. Okay, so saying I conducted a between subjects t-test to examine possible differences in mean scores for participants, n equals 100, we had 100 participants, who received the relaxation activity compared to those who did not. The results illustrated a significant difference between groups, and here's what you would actually put down, and I'll go over this in SPSS in class too. T99 equals 3.1, P is less than 0.01. The relaxation activity appeared to significantly decrease anxiety. Okay, so First question, how did I come up with a 99 in the parentheses? Well, that is n minus 1. In a t-test, that's a degrees of freedom. And you subtract 1 from your total n, from your total number of participants. That's your degrees of freedom. It's really simple in a t-test, n minus 1. Basically, it's telling you our t-statistical is 3.1. And the probability of us making an error, saying that this score is not significant, is less than 0.01. Now, we usually talk about 0.05, but in this case, it was, it's way out there in the tail. And that's 0.5 would be, 0.05 would be about right there. Well, somewhere around 2, maybe a little above 2. But, so we did some good things. We found some significance. Last thing, some of you are going to run ANOVA or maybe even multiple regression. And so when we report F-scores look at a distribution a little differently. We're looking at many different, more than one group of people. So for instance, let's say we added a group in our experiment above. So let's say that we added from the above relaxation activity, we added participants who tried the relaxation activity via ITV. In other words, the researcher didn't do it in person with them. They piped it in, via technology. The researcher then found these 3 scores by adding that third group. Anxiety scores of students who had the relaxation activity in person. Their mean score was 3.2, pretty low. Anxiety scores of students who were given the relaxation activity via ITV. The average there was 4.2. And then anxiety scores of students who were not given a relaxation activity. Again, those were 4.5. So we would run ANOVA to actually compare the differences between those 3 groups. Okay, you can't run, you could run t-test, but really it's not appropriate in this case. You're supposed to run ANOVA when you have 3 or more groups. And so let's say that we run the ANOVA and we come up with an F-score of 4.481. So here you can see that F-score, if you get about 2.5, 3 above, you're getting out here in this small percentage. Again, this represents the F distribution. It doesn't look normal, but this, when you have 3 or more groups, is what you have to work with. You can't go with the bell curve. And so you're still, same thing. If you had a score of about 1, you're looking at most of the population right there. Most scores should be 1 or less. So if you have a score of 3 or more, you're probably going to be significant. So in this case, we had an F score of 4.481. Let's look at how we would report that and how do we make sense of that. So here's how we would report it. I conducted a one-way between subjects ANOVA to compare differences between groups of students who received the relaxation activity face-to-face, via ITV, or did not receive a relaxation activity. Results of the ANOVA revealed significant differences, differences between groups. Here's the important part. F2, 97 equals 4.481. P is less than 0.01. Okay, first question. Where did I get the 2 and the 97? Okay, so those of you that pay attention for the T, you're like, those are the degrees of freedom. And the degrees of freedom in this case come from this right here. The first one comes from K minus 1. So K equals the numbers of groups. And then your second one is N minus K. Your total number of participants minus the number of groups that we had. So we had 3 groups, 1, 2, 3, had 100 participants, subtract 3, we come up with 97. We had 3 groups, minus 1, we come up with 2. That's where you come up with those. Those are important because they tell you, and they tell researchers what sort of F-score you need to be significant. So that's what those mean. So basically what you're saying is when we had 3 groups and 100 participants, our F-score was 4.481. The probability of that being found by chance is 0.01, which means it is statistically significant. Now, last question. What if there is not significant difference between ITV and the control group who had no relaxation activity?